We are on 7.2 and we're looking at the transport of oxygen by haemoglobin. Last lesson we looked at the shape of the curve. It's called the oxygen dissociation curve, and it shows how oxygen associates or dissociates with haemoglobin as the partial pressure of oxygen changes. And we said that this is perfect. It's perfect for us as humans because at this point here, the partial pressure of oxygen is high. Haemoglobin is hanging on to that oxygen, and indeed that's what we want it to do at the lungs. When the partial pressure of oxygen is high, haemoglobin hangs onto it. At partial pressures of oxygen that are low, in other words respiring cells, we want the oxygen to become free. We want the haemoglobin to dissociate from the oxygen and to dump it so that it's available for cells. And so at low partial pressures, it's free. We've got this much being held on by haemoglobin and this much being free to cells. So a perfect situation. And if we think about it in common sense terms, it always makes sense to us. Let's now think for a moment about how carbon dioxide would ideally change that curve. Let's think, at respiring cells, we have a higher partial pressure of carbon dioxide. If we've got a higher partial pressure of carbon dioxide, we want our haemoglobin to dump our oxygen more readily. Because if there's a high level of carbon dioxide, then that means that there must be more respiration going on, and therefore we need more oxygen. So going back to this graph, we've got our normal physiological range where oxygen is in a high partial pressure at the lungs. This would be the carrying capacity of the haemoglobin. When it gets to respiring cells, where it has a lower partial pressure, the haemoglobin drops off the oxygen, and so its saturation is less. Let's consider the Bohr shift. The Bohr shift describes the shifting of the oxygen dissociation curve to the right. Now it makes sense to us that in an area where there was high carbon dioxide levels, we would want our haemoglobin to dissociate from the oxygen. Reason why, if we've got high carbon dioxide levels, we must have a high level of respiration. If we have a high level of respiration, we need oxygen. So we don't want haemoglobin hanging on to that oxygen. We want the haemoglobin to dump it, to dissociate, to unload it, ready for the tissues. So let's have a little think what this curve actually means and what it actually shows. Let's consider, remember this is our partial pressure of oxygen and this is our percentage saturation of haemoglobin. Let's just work on this level here of partial pressure of oxygen. And let's imagine that this red line actually represents the normal dissociation curve. So at this level of saturation, let's call it a partial pressure of 3, then the haemoglobin is got this much attachment to oxygen. It's saturated up to there. If there's a high level of carbon dioxide, however, that is shifted to the right. And now, if we look, the haemoglobin is only saturated to this amount here. And so that means that all that oxygen is therefore released to the cells. So the Bohr effect, or the Bohr shift, has lowered the affinity for haemoglobin to oxygen because we need a much higher partial pressure of oxygen before haemoglobin will bind to it. And this is perfect for our cells. Whenever respiration is taking place, the oxygen levels decrease, the carbon dioxide levels increase. So we've got 2 triggers basically that are telling our haemoglobin to dissociate from the oxygen, to unload the oxygen and make it available to respiring cells. And as we can see on this graph, we've got a partial pressure of carbon dioxide of 6 kilopascals and a partial pressure of carbon dioxide of 3 kilopascals. So as we increase the carbon dioxide, we shift that whole curve to the right. Here's another graph, and it shows the oxygen partial pressure at the top, and it's just turned it into percentage at the bottom. It's got a range here which shows where most of other mammals, where their saturation curves live, and then it's got two other curves showing a llama and a vicuña. And basically they live at high altitudes, so we need them to have a really high affinity for oxygen. And you can see that has shifted the curve to the left. Carbon dioxide shifted it to the right, but what we want is when you're living at high altitude, you want your haemoglobin to have a high affinity for oxygen, to grab onto it at low partial pressures. So again, if we just look at what that graph means, it means that at a partial pressure of 20%, or 20 rather, there, if we go up, normal mammals would only have, with this kind of range of saturation. However, for an animal living at altitude, a lot more of their haemoglobin would be saturated with oxygen. And here's another graph that shows, here's our adult haemoglobin. Again, we've got our sigmoid, our S-shaped curve. And this shows us fetal haemoglobin. Haemoglobin that's in the unborn baby. Now clearly, baby gets its oxygen from mum. Mum's haemoglobin is carrying it around the body. And so the fetal haemoglobin has to have a higher affinity for oxygen to be able to pull the oxygen off the maternal haemoglobin onto the fetal haemoglobin. And so that is shown on this graph by shifting the curve to the left. Whereas the carbon dioxide shifted it to the right, the fact that it's maternal haemoglobin and fetal haemoglobin pulls it to the left. And if we just have a think about what that actually means. At a partial pressure of 5 here, when we look at adult haemoglobin, it's only that saturated with oxygen. When we look at the fetal haemoglobin, if we carry it up at the same partial pressure, fetal haemoglobin is a lot more saturated with oxygen. So it has a higher affinity for it, it's going to load a lot easier, but it's going to unload less easily. Here are a couple of haemoglobin dissociation curves. Here's one for a human, and it shows the Bohr effect, how it shifts to the right with increased carbon dioxide. Oops, let's go back. With increased carbon dioxide, it shifts to the right. And the same is true with crocodile haemoglobin there. There's a shift to the right and a slightly different shape of curve when there's carbon dioxide or when there's no carbon dioxide. Okay, let's have a look at this exam question from January 2010. It's from the old legacy material, but it still stands. Question 4. An increase in respiration in the tissues of a mammal affects the oxygen dissociation curve of haemoglobin. Describe and explain how. So there's 2 marks, so we're going to get 1 mark for describing and 1 mark for explaining. Let's go back to the root of the question. It's asking, how does it affect the oxygen dissociation curve? Well, it moves it to the right. And we know that because that's the Bohr shift. When we have a higher increase of carbon dioxide, it moves to the right. So we're going to say, moves to the right because there's more carbon dioxide due to increased aerobic respiration. Next part of the question asks, there is less oxygen at high altitudes than at sea level. People living at high altitudes have more red blood cells than people living at sea level. Explain the advantage of this to people living at high altitude. Well, we're going to say that if there are more red blood cells, that means that there's more haemoglobin. And this means that more oxygen can be loaded at the lungs. In the examiner's report, they wouldn't accept you saying that this means more oxygen can be transported around the body. And I guess this is because if there was a higher partial pressure of oxygen, more oxygen would be able to be transported around the body. The fact that we've got more red blood cells just means that we can load more oxygen at the lungs. The next question says the graph shows oxygen dissociation curves for people living at high altitude and for people living at sea level. And we can see that living at high altitude from the graph has a similar effect of having a high carbon dioxide level. It makes it harder for the oxygen to bind to the haemoglobin, which means it's lowered its affinity for it. So if it's got a lower affinity for it, it's more likely to be dropping it off, the oxygen that is, and that's exactly what we want. We want the haemoglobin to be dropping off oxygen more easily at a lower partial pressure of oxygen, so that there's more oxygen available for respiring cells. Now, taking another look at that graph, I just want to make a couple of points. An increase in altitude or an increase in carbon dioxide moves that curve to the right. It makes oxygen easier to dissociate from haemoglobin. And that's because our haemoglobin is our haemoglobin. And just moving the partial pressures of oxygen or changing the altitude or the carbon dioxide will move that to the right. However, other organisms have different haemoglobins that are permanently placed more to the left. And by placing it more to the left, it means it has a higher affinity for oxygen. And so therefore, it is able to load more oxygen at a lower partial pressure. And by shifting the oxygen haemoglobin dissociation curve to the left, what we're showing is that haemoglobin has an increased affinity for oxygen, which also means it's harder to let it go. We have to have a really low partial pressure of oxygen before it lets go. I hope that makes sense to you. Sometimes you have to look at this several times with fresh eyes and rationalise it from the very beginning. It is a subject that can be quite confusing. Thanks for watching, and don't forget to leave me a comment.